This class discusses discrete random variables and some related concepts. A random variable is a quantitative variable whose value depends on chance. For example, roll a pair of 5 dice. The sum of the dice is a random variable. The number of puppies in a litter is also a random variable. Other examples include the return on an investment and the lifetime of a flashlight battery. A variable can be discrete or continuous. We can also have discrete random variables and continuous random variables. Right now, focus on discrete random variables. We will discuss continuous random variables later. A discrete random variable is a random variable whose possible values can be listed. In particular, a random variable with only a finite number of possible values is a discrete random variable. For the above examples, the sum of dice and the number of puppies are discrete random variables. The return and lifetime are not discrete random variables. We usually use capital letters such as X to denote a random variable. Use small letters to denote a possible value of X. The notation X equals X with curved brackets indicates the event that the random variable X equals X. The notation probability of X equals X denotes the probability that the random variable X equals X. To be rigorous, we may need a pair of curved brackets in the notation of probability. However, we ignore those for simplicity of notations. A discrete random variable can be characterized by its probability distribution. The probability distribution is a list of the possible values and the corresponding probabilities of a discrete random variable. Sometimes the probability can also be expressed in terms of a formula. For example, a group of students were asked how many siblings they have. The left table lists the frequencies of the number of siblings. In this example, the number of siblings of a randomly selected student is a random variable. Use letter X to denote this random variable. X has 5 possible different values, ranging from 0 to 4. The right table lists the probability distribution of X. It lists the probability of each possible values of X. For example, probability of X equals 0 is 0.2. Probability of X equals 1 is 0.425, and so on. We can see that the sum of probabilities equals 1. We may use a histogram to display the probability distribution. In this case, the histogram is called a probability histogram. It is essentially the relative frequency histogram we discussed before. Each bar in the histogram indicates one possible value of the random variable. The height of the bar is proportional to the probability. The bottom figure is the probability histogram of the number of siblings of a randomly selected student. From this histogram, we can see that there are 5 possible values. The value 1 has the largest probability, and the value 4 has the smallest probability. The most important property of a discrete random variable is that the sum of probabilities for all possible values equals 1. We can use this property to find any missing probability. In this example, the distribution of X is given in terms of table. We can see that X has 4 possible values, 2, 4, 8, and 10. We know the probabilities of 3 of them. The probability of 8 is missing. Because the sum of the probabilities equals 1, the probability of 8 is therefore 1 minus the remaining probability. 1 minus 0.2 minus 0.1 minus 0.3, which is 0.4. If we want to calculate a probability involving a discrete random variable, we need first to identify which possible outcomes are included in the event. Then add the corresponding probabilities together. For example, what is the probability that the absolute value of x minus 5 is less than or equal to 3? We first need to find which values of x satisfy this inequality. Notice that x has only 4 possible values. We may simply replace x by each of its values to see whether the inequality holds. We can find that only 2, 4, 8 make this inequality hold, and 10 does not make this inequality hold. Therefore, we add the probabilities corresponding to the value 2, 4, and 8. That is, the probability is 0.2 plus 0.1 plus 0.4 equals 0.7. In this example, we consider the experiment of tossing a balanced coin 3 times. There are 8 possible outcomes. In the following, we use H to denote heads and T for tails. The 8 possible outcomes are listed. Let X denote the number of heads. It is a discrete random variable with 4 possible values, ranging from 0 to 3. What is the probability of X equals 2? There are 8 possible outcomes, equally likely. 3 possible outcomes lead to 2 heads, that is TTH, HTH, THH. Therefore, the probability of X equals 2 is 3 over 8. One may ask how we know that 8 possible outcomes are equally likely. We can get this using the special multiplication rule. Recall the example of roulette we discussed earlier. The 3 tosses are independent of each other. Therefore, probability of HHH equals probability of H times probability of H times probability of H. We know that probability of H is 0.5. Therefore, probability of HHH equals 0.5 to the power of 3 equals 0.125. Similarly, the probability of each outcome is 0.125. Therefore, the 8 possible outcomes are equally likely. We have calculated probability of x equals 2. We can calculate the probability of other values. The probability distribution x is given in the table. Probability of x equals 0 is 0.125. Probability of x equals 1 equals probability of x equals 2 equals 0.375. Probability of x equals 3 is 0.125. What is the probability of x less than or equal to 2? This event includes 3 possible values of x, that is 0, 1, and 2. We need to add the corresponding probabilities together. 0.125 plus 0.375 plus 0.375 equals 0.875. Therefore, the probability of x less than or equal to 2 is 0.875. We have mentioned before that a probability can be explained in terms of a proportion over long-run repetitions. For example, let x be the number of heads when tossing a balanced coin 3 times. We may repeat this experiment many times, for example, 1,000 times. For each time, we record the number of heads. The results of 1,000 experiments can be summarized in this frequency table. It lists that 136 times out of 1,000 experiments, we get 0 heads. 377 times for 1 head, 368 times for 2 heads, and 119 times for 3 heads. The frequencies divided by 1,000 yields the relative frequencies or proportions. Compare these proportions with the probabilities in the previous slide. They are very close. In fact, if we increase the number of experiments, for example, 10,000 experiments, the proportion will be even closer to the probabilities in the previous slide. As a summary, in a large number of independent observations of a random variable x, the proportion of times each possible value occurs will approximate the probability distribution of x.